I'm here to talk about something that you all know about, so that is pH and draining. And to do that, I'm going to introduce you to two cheeses, cheese A and cheese B, both made in small batches for the purposes of demonstrating the effect that pH and drainage will have on the finished properties of the cheese. We're going to come back to these cheeses a little bit later on and discuss the exact reason for the difference between the two, but you'll see that cheese A is acidified more. It's showing more breakdown around the rind. Cheese 2 is higher acidity, we would assume. Is showing more elasticity, more colour, more yellow colour. So first of all, I'd like to talk about the way that we think of pH. Now, I visit a lot of cheesemakers, and one of the things that comes up very often when I ask them about their pH profile, they all say, well, I hit 5.2 at 24 hours, so I ticked the box, and the CCP has been met. Which, okay, I get that. But in looking just at pH as a food safety mechanism, we're missing out on so much more, because it also has a big effect on rennet coagulation properties, for example, the moisture content contained within the cheese. And if we do actually start to look a little bit more closely at the use of pH to be a CCP, it isn't actually always that effective. So a report that I've written into coagulase positive staph growing in 2 soft cheeses will be published in the next SCA newsletter, and you'll see this graph here. This was a trial in which I was trying to validate a new milk supply which had very high staph levels in the initial milk. So the initial milk on this particular make was 480 staphs per mil, which, okay, that's a bit higher than the SCA target of less than 100. But we were also seeing similar growth when the staphs were brought down to 30 per mil. We were seeing similar growth when the staphs were down to 50 per mil. And what we're actually seeing at 2 days, we have about 4.5 to 5 log of cheese. So coming up from 2 log, essentially we've got a 2 log growth. And that is probably happening in the first 6 hours or so, before the acidification has actually started. These particular starters were rehydrated ahead of time in milk, so they hit the ground running, and they should have started to get going a little bit sooner than something like a dry DVI, open the packet, put it in. In theory, you know, you'd expect to see a very long lag time there. The staph is already active. It's been in the udder. It's starting to multiply. It's going to grow faster. So a good demonstration that achieving a certain pH isn't always going to be an effective CCP. We've got, we have here the semi-soft achieved a pH of 5.4 within 6 hours. It was a higher pH, but it got there faster. The lactic cheese, which achieved 4.6 within 12 hours, it was higher to begin with, up here, because it was a much slower make. However, when it started to come down, because the pH was low, it was coming down a bit faster. But even so, these kind of figures we don't really want to be seeing in a cheese, because as that cheese starts to ripen, as the pH starts to come back up again, we could see those staphs going back up. And then we look at an investigation that I did 2 or 3 years ago into textural defects in a hard cheese. So I took all of the cheeses that had graded particularly well and all of the cheeses that had graded badly, and I started to break down the individual pH profiles. And as you see from the graph, there's not actually a lot of difference between good batches and bad batches. They're all in the same kind of area. You're looking at the start at about 0.2 of a pH point difference between any individual batch, and roughly the same at the end as well. There is only one point on that graph in which there is a significant difference. And when I started to look, everything that appeared above that space graded well, and everything that appeared below that space graded badly. Now, that's not to say that's going to be the same with every cheese that you make. You make different cheese types, you might get different points in the pH graph making differences to that cheese. But it's also important to look at the fact that the 0.2 of a pH point, you know, at the start of the make, that didn't make a hell of a lot of difference. At the end of the make, it didn't make a hell of a lot of difference. But there is one critical point during the make at which a tiny little difference can produce quite a substantial change in the end product. Which brings me to an animation which simplifies what's actually happening in the curd and should show you, essentially what's going on. What we have here, all of the caseins, which are kind of bound up with calcium phosphate, which acts as a kind of elastic glue between all the caseins. So cheeses that retain a lot of calcium will tend to be very elastic cheeses. Cheeses that lose a lot of calcium will tend to be less elastic. So, as we're starting to acidify, we're producing hydrogen ions, protons, and they're going to start displacing the calcium. And this continues until we reach a point at which we decide we're going to drain the whey off. So at that point, we're taking away everything around. We're also losing half of my text, but there you go. One of the key points that I want to make here, you've got the acidification proceeding as the curd is continuing to acidify. You've got calcium kind of locked up within the body of the curd. If there is a lot of whey trapped within that curd, you're going to drain that calcium out with the whey. If you've already got pretty dry curd, you're going to tend to hang on to that calcium. So, it's not so much that the cheeses that we looked at earlier, the cheeses A and B, it's not so much that one went particularly lower than the other. If you actually look at the acidification curves, they were pretty similar. Cheese A might have been a little bit lower, but it wasn't a hell of a lot lower. And so we really have to look more at what kind of calcium drainage and pH issues are going on there. So going back to all of the different factors that would be influenced by pH. First of all, pH is going to affect rennet coagulation properties. So the lower the pH, the faster the flocculation is going to happen. If you're making cheese by the clock and you're not taking into account differences in flocculation time, you're actually going to end up hardening the curd more. You're going to lock in more moisture, and you're going to push it more in the direction of cheese A. If we look at ripening, and we'll have a look at the pictures in a moment. In fact, if I move on now, we see from cheese A that there is a lot of breakdown around the outside. The paste has a very low pH. Pretty much all of the breakdown is associated with the area immediately under the rind, and as a result, the rind is slipping off from the cheese, which we don't see in cheese 2. There is a greater similarity between the rind pH and the core pH. So, rind slipping on cheese 1, low core pH, high rind pH, very inelastic paste, essentially plastic paste. People often talk about plastic cheese. What they actually mean generally is elastic cheese. Cheese A is a plastic cheese, cheese B is elastic. The size of the cheeses is also worth looking at. Cheese A has shrunk more in the molds, it's thinner. Basically, the same amount of curd went into the molds, but cheese A had a lot more moisture contained within each curd particle, so as it drained, it shrank down more. And the difference, I could have done lots of things to achieve this difference, but the difference that I made here, I cut the curd to 1 centimetre cubed in the case of cheese A, so less surface area, more moisture contained within the curd. And cheese B, I cut that to 0.5 centimetre. I could have increased the hardening time of the curd with cheese A, and that would have achieved a similar kind of result. So, we talked a little bit earlier about people who make cheese by the clock. Let's say that you are pretty much following a kind of clockwork cheese making process, and at different points in the year you'll get different results. I saw one reference on the internet quite recently to someone who makes a blue that is seasonally blue, and I'm guessing that this has quite a lot to do with it. So we have different urea contents in the milk throughout the course of the year. Through the winter, we tend to have very low urea, which would be less than 0.01. Through the summer, we tend to have high urea, which could be 0.04, 0.045, somewhere like that. If we are working to a set time, and bear in mind, you know, with cheese making, it's going to take a period of time to achieve all your processing steps to get the curd to the right kind of feel and texture. So even if you're not making cheese by the clock, but you're not entirely aware of how the acidification is racing away in the winter, you can still end up with acidification defects, very white cheeses made during the winter, lots of acidity, uneven breakdown, so lots of ripening around the outside. And all of that could simply be controlled by more careful monitoring of the pH. Now, when I said that I wanted to talk about pH and drainage, Bronwyn issued a word of caution, which was that a lot of people are incredibly fearful of pH. You know, when I visit people, the pH meter is broken, is something that I hear quite a lot. It's giving readings that I don't kind of understand, so therefore it must not be working. So, how do you look after a pH meter? First of all, cleaning as you go along is vitally important. If you leave the pH meter sitting in the sample for half the afternoon, don't expect it to still be working 6 months later. Calibrate the pH meter before use with pH 4 and 7 buffers. Remove the electrode, as I said, from the sample, rinse it with warm water. Replace the buffers every month. You know, have a little pot that you top up with a litre container of buffer. Change that regularly. In terms of the voltage readings that you get with a pH meter, some meters will have the ability to read in millivolts. If you put your probe into pH 7 and it reads 0, plus or minus 30 millivolts, then, okay, that buffer is fine, or the pH meter is fine. If it's not actually reading within those parameters, first of all, change the buffer, and if that doesn't work, change the electrode. The slope on the pH graph, some meters, once again, will give you a slope. So basically, for every pH point that you increase, so going from pH 4 to pH 5, you will go up, you will go down 58 millivolts, plus or minus 3 millivolts. If your slope isn't within those parameters, once again, change the buffers, change the electrode if it doesn't work. You would expect a shelf life on an electrode that's being used reasonably frequently but is well cared for, I'd say somewhere between 6 months and 1 year. That wouldn't be unreasonable. In terms of cleaning, green detergent, Fairy Liquid, multitude of uses, as I was saying to someone this morning. Clean it off with Fairy Liquid, you'll dissolve off a lot of the fats. If you start using pepsin and acid-based cleaning products, that's where a lot of problems can arise. The more you use them, the more you're going to damage the electrode. So you're going to shorten the life if you're using a lot of quite harsh chemicals to clean it. Once you've cleaned it, rehydrate the electrode in a buffer for about 1 hour. I saw one person who was actually putting it into cleaning solution rather than storage solution every time they'd just taken a reading, and as a result, all the readings they were getting didn't make any sense at all. Finally, if the reading starts jumping around erratically, well, it might not be the kind of electronic part of the meter that's broken, but once again, replace the electrode. As soon as the readings are jumping erratically, it's very likely that you've got a blocked reference electrode. Basically, the meter has become blocked. It's not working anymore. If you probe your curd directly, you'll probably find you're going to block the reference quite a lot. If you're taking whey samples and you're checking those, you might not block it so often. I'm about to talk about TA, but I should probably talk about pH paper first, because I sometimes get into trouble for not giving pH paper its due attention. pH paper has a tolerance of about plus or minus half a pH point, which could be anywhere between dangerously under-acidified and completely over-acidified. And if that's good enough for your cheese, please use pH paper. Otherwise, pH meter, works very well. TA works very well, but we don't always use TA properly either. The end point that I often see people titrating to resembles something like strawberry milkshake. And at that stage, you've gone way too far. The pH endpoint, the phenolphthalein endpoint, has a pH of 8.3. If you put the pH meter into your sample and you're reading 8.3, assuming that your pH meter was working properly in the first place, that is the endpoint. You'll be able to titrate to 8.3. If you're training new staff, you can get them to titrate to the same endpoint. They can actually learn what that endpoint looks like. Don't go all the way through to pH 8.91. One of the key things about pH 8.3, for every drop of sodium hydroxide that you put in after that endpoint, you're actually going to push the colour quite a lot. One drop is going to move that pH, and it's going to move the colour very quickly. It becomes very hard to determine between the true endpoint and an excess of sodium hydroxide. So, back to cheese A and B. With artisan cheese making, we would accept that there is going to be a certain amount of batch variation. Jamie talks a lot about batch variation and celebrates batch variation. But when you buy a Monty's, you're pretty sure that you're going to get something that looks like Montgomery's cheddar. You're not going to expect to open it up and find that you've got Applebee's Cheshire instead. So we have to really think about what is an acceptable and an unacceptable batch variation. And if I was making cheeses A and B and sending them out to a customer, I could understand that they'd start getting pretty miffed if half of cheese A was melting through the rack and cheese B was just too firm and had no flavour at 2 months old. So it is very important that we monitor pH throughout the course of the drainage, look at how much calcium we're actually removing and whether we're getting the kind of lifting rind problems that we've got here. And also be aware, I would say, that variation not only happens between batches, in some cases it actually happens within the same batch. And in some cases, you can actually get variation within the same cheese. It's really worth trying to make sure your pH and your drainage are consistent throughout the whole batch. Thank you.